Hello students, welcome. Previously, Form 4, Topic 2, Lesson 5, we were dealing with molar enthalpy or molar heat of combustion. So in Lesson 6, we are going to do number 3, that's molar heat of displacement. So what is heat of displacement? So this is the enthalpy change that occurs when a substance is displaced from a solution of its ions. Okay, what about molar heat of displacement? This is the enthalpy change that occurs when 1 mole of a substance is displaced from a solution of its ions. Remember, students, we have done previously displacement reactions, and displacement reaction was a reaction in which a more reactive element displaces a less reactive element from its solution of its ion. For example, if we are having a CO2 sulfate solution, then it's reacting with magnesium metal, which is a solid. We are going to have their displacement reaction because magnesium displaces copper from its solution, and we are going to have magnesium sulfate and copper metal. So we go examples. Example 1, we are told when 100 centimeter cube of CO2 sulfate solution was added to 4.0 grams of zinc powder, the temperature rose to 24.5 degrees Celsius. So from here 1, we are told determine the equation for the reaction. So the reaction is in between CO2 sulfate and also zinc metal. So we are going to have CO2 sulfate. So here it is aqueous reacting with zinc metal, which is solid. We are going to get zinc sulfate aqueous, and we are going to get copper metal. So in case you are told write an ionic equation, it is another question like you are going to remove the spectator ions. So we are going to have CO2 ions aqueous reacting with zinc metal solid, and we are going to get zinc 2 ions aqueous and also copper metal and copper solid. So this is when you are supposed to require to write an ionic equation. Okay, number Romeo 2. We are told determine the molar heat of displacement of copper. So the same procedure that we are dealing with when we are dealing with molar heat of solution, molar heat of combustion. If you want to get molar heat of displacement, the procedure is the same. You have to get first of all the enthalpy change. So we said enthalpy change is given by mc delta T, where m is the mass of the solution. Here we are having 100 centimeter cube. That means we are going to have 100 gram times 4.2 as my specific heat capacity times the temperature change. We are having here 24.5 because we are told the temperature rose to divided by 1000, so that we convert it into kilojoules. So I'm going to get 10.29 kilojoules as my enthalpy change. So the next procedure is for us to calculate the number of moles. So here copper, I'm given 100 centimeter cube of 0.5 mole. So here we are missing 0.5 mole CO2 sulfate. So we can get moles. Moles is given by molarity times volume used over 1000. So in our case, our molarity is 0.5 times our volume used is 100 divided by 1000. Here we are going to get 0.05 moles. Okay, from there, we are going to ask ourselves, this number of moles produces what amount of energy? That means 0.05 moles produces 10.29 kilojoules as the energy. So we ask, what about 1 mole? So we cross multiply 1 times 10.29 divided by 0.05. So here we are going to have 205.8 kilojoules per mole. Next, let us see the sign that we are going to put in front the number. That one will tell us now the temperature. If you see a rise or rose, that's an exothermic reaction. We are going to put a negative sign. In case you see the temperature drop, we are going to put a positive sign because that will be an endothermic reaction. So, but B, we are told why, explain why excess zinc powder was added into the beaker. This is displacement reaction. So the answer will be in order to completely react with the CO2 ions. So we are going to say, in order to ensure that all copper 2 ions, all the copper 2 ions are displaced displaced from the solution by the zinc border. So that's from your C. We are told give a reason why the molar heat of displacement in this experiment is lower than that of the theoretical value. This is just the same when you are dealing with the enthalpy of solution, enthalpy of combustion, enthalpy of displacement. We are going to say one heat energy, or we can say some heat energy is lost to the apparatus, Number 2, we can have again some heat energy is lost to the surrounding, surrounding, which is not accounted in the calculation, making the molar heat of displacement in this experiment lower than the theoretical value. That means the values that are quoted in the data books or in our KLB books. Okay, next we are going to have question number 2. In question number 2, the question reads like this: in an experiment to determine the molar heat of displacement when magnesium displaces copper, we are told 0.6 gram. So here it's supposed to be 0.6 grams of magnesium powder were added to 25 centimeter cube of 1 mole of copper 2 chloride solution. The temperature of the solution increased by 43 degrees Celsius. So from here A, we are told, other than increase in temperature, state and explain the observations made. So for you to know the observation in chemistry, it is good for the students to write the equation that's taking place, either a chemical equation or an ionic equation. So to write this chemical equation, it will be, we're having copper 2 chloride aqueous reacting with the magnesium powder. We are going to get, this is solid, we are going to get magnesium chloride aqueous and also copper metal solid. Here we are having two observations. One of the observation is that initially copper 2 chloride is blue in color because it's having copper 2 ions which are blue in color. But when you come to this side, this magnesium chloride is a colorless solution. So one observation is the blue color of the solution fades. But the other observation that we can see here is copper being deposited, and the color for copper metal is red-brown. That means a red-brown solid is deposited. That's the other observation that you have there. So let me just write one, so we can say blue color of the solution fades, or you can say as well as disappears. Reason, because you have to explain. This is because copper 2 ions are displaced from the solution by the magnesium. And that copper 2 ions were the ones that were responsible for the blue color, or that were giving that solution the blue color. Once they are displaced or they are removed from the solution, that means the solution will not have that blue color. So instead, it's going to fade or disappear. Okay, if you want, you can use the other observation as red-brown solid is deposited, and the reason will be because copper 2 ions are reduced to copper metal by the magnesium. Okay, next but B, we are told determine the molar heat of displacement of copper. So the molar heat of displacement, we have to start first of all getting the enthalpy change. So enthalpy change is given by mc delta T. So our m here will be 25. That's our volume given. So we are going to multiply by the density of solution, which is 1 gram per centimeter cube. So we are going to get 25 gram times 4.2 as my specific heat capacity times 43 as the temperature change divided by 1000 so that I convert it into kilojoules. So we are going to get 4.515 kilojoules. That's the first step when you're told get the molar enthalpy of displacement or molar of solution, molar enthalpy of combustion. The first step, you have to get the enthalpy change. So we have gotten it in kilojoules. Next, we have to go to the moles. We have to get number of moles. So here we can get molarity. The formula as molarity times volume used over 1000. So here the molarity is 1 mole, as you can see there. 1 times the volume here is 25 divided by 1000. So here we are going to get 0.025 moles as our number of moles. So thereafter, we are going to ask ourselves, this amount of moles, this moles produces 4.515 kilojoules as energy. So what about 1 mole? So we are going to say 1 times 4.515 divided by 0.025. So here we are going to get 180.6 kilojoules per mole. Next, let us see now the sign that we are going to put there, and that one will tell us now the temperature. We are told the temperature of the solution increased by 43. So if the temperature is increased, that's an exothermic reaction, and exothermic reaction is given negative sign. So in number 3, we are told in a double decomposition the reaction, 900 centimeter cube of 1 mole copper 2 sulfate solution were mixed with the 600 centimeter cube of 1 mole barium chloride solution. The equation for the reaction is as shown below. Copper 2 sulfate plus barium chloride, we get barium sulfate plus copper 2 chloride. So this is the enthalpy change, the molar enthalpy of this displacement. Okay, we are told which substance was completely used in the reaction. So here, as you can see, this reaction is self-balanced. That means 600 centimeter cube of 1 mole barium chloride will be the one that will be completely used in the reaction, because the other one, copper 2 sulfate, is still having 300 centimeter cube. So we are going to write barium chloride. Barium chloride will be the one that will be completely used in the reaction. So calculate the number of moles of the substance used in A above. So we are going to have number of moles. The formula for calculating number of moles was molarity times volume used over 1000. So this will be equal to molarity, which is 1 times 600 as my volume used divided by 1000. This is 0.6 moles. So next we are told calculate the amount of heat evolved by the number of moles obtained in B above. Check here, we have been given the molar enthalpy of this reaction. So we are going to say 1 mole produces 17.7 kilojoules. So we ask ourselves, what about 0.6 moles? What amount of energy can it give us? So it will be 0.6 times 17.7 divided by 1. So this will be equal to 10.62 kilojoules as the energy. Then lastly, we are having part D. Part D, we are told to calculate the temperature change for the double decomposition reaction. The temperature change for the double decomposition reaction to the nearest whole number. Specific heat capacity is given 4.2 joules per gram per Kelvin. Density of solution is 1 gram per centimeter cube. So let's start with the enthalpy change. Enthalpy change is given by mc delta T. So let's start with mass of the solution. Mass of solution. This will be equal to, if you check, we are having 900 centimeter cube of 1 mole copper 2 sulfate. So that's 900 plus, we are having the other side again 600 centimeter cube of 1 mole barium chloride. So plus 600 centimeter cube, this will be 1,500 centimeter cube times 1 gram per centimeter cube. We are going to get 1,500 grams. So using the formula, we have gotten enthalpy change as 10.62. Yeah, we have gotten 10.62. So we are going to say 10.62 will be equal to 1,500 grams times 4.2 times the temperature change that we don't have divided by 1,000, because this enthalpy change is in kilojoules. So we are going to say times 1,000 here, times 1,000 here. So that means we are going to get 10,620, which will be equal to 6300 times delta T, temperature change. So if you want to get temperature change, we are going to divide here by 6300, and here we are going to have 6300. So temperature change here, we are going to get 1.69 degrees Celsius. So to the nearest whole number, temperature change will be 2 degrees Celsius. So that will be the temperature change for the double decomposition reaction to the nearest whole number. Next, we are going to have the extended question. We have one question for extended questions. That's the end.